Okay, so Feynman's theorem, which is pretty well erased at this point. I might as well finish it off. So Feynman's theorem gave us, for the integers, a rough structure theorem for sets with small doubling. And there, really, the key structure is just this notion of a generalized arithmetic progression. Right? Those things have small doubling. Anytime you have small doubling, you're either one of those or some fraction of one, 50% or 20% or something like this. Now, we're interested in these kinds of theorems in all sorts of settings. I'm going to aim toward this theorem due to Rouges, which gives us a structure theorem for small doubling that works in groups where every element has bounded order. Now, of course, if every element has bounded order, we're not going to see nice, long, rich arithmetic progressions. They just don't exist. In this case, the only thing that can happen is your whole group, or your whole set A has to be trapped inside a small subgroup.
So is T equal to C?
Yes. Yeah. Shoot. Yeah. I will try and, yeah, there was some confusion. Yeah, okay. So there we are. That's much better. Okay, so you have a set with this small doubling. When you add A to itself, the size of this new set is at most T times the size of the original. Then what's going to happen is there's got to be a subgroup H that's that kind of efficiently captures your set, right? So this A is going to be a subset of H. Your set A is completely trapped in this subgroup, and the order of H, it's some controllable amount larger than the size of the original set A, right? So certainly, if I tell you that A is a subset of some subgroup H, and the size of H is at most this, that's giving you some control on how big the double of A can be, right? Because the double of A still has to sit within H. So if you have this structure, then I know that twice A will only be this much as a factor larger than the original size of A. Right? So this is that kind of rough structure theorem that I'm talking about, right? So here we have, you start out with a set for which twice A is at most T times the size of A. And then I'm going to deduce that you have a particular structure. And the structure that I get, this structure implies that your set has small doubling. This structure implies that the size of twice A is at most T squared R to the T to the fourth times the size of A. Right? So this is the essence of a rough structure theorem. So we've got a notion that we care about. This is small doubling. This small doubling implies that we have a certain structure. And that structure implies that you have small doubling. Only, as you're seeing, I mean, T here has gone to R to the T to the fourth. I mean, this is exponential. This is bad. We'd much prefer a tighter structure that came with some kind of polynomial bound. And that's still an unsolved problem, and a very meaningful one that, I mean, I think it's just a fantastic problem, really, in pure combinatorics.
So they think it could be
so I should be clear. If you just wanted this structure, you just want some subgroup that captures your whole set, then you're necessarily going to have a bad exponential bound. What we'd like is some finer structure that's sort of better tuned to A, that then implied you had smaller doubling with a better constant. So you can't hope just to capturing the whole set just in a subgroup is crude.
To me, this bound looks great. It's constant, right?
Well,
are constants, right?
Well,
yeah.
Well, that's true. I mean, I mean, the truth is, a lot of applications have that form, and this is already great. Yeah, but sometimes not. I mean, so this sort of additive combinatorics world, there are lots of applications of these kinds of theorems. This is really kind of these are theorems that really get a lot of mileage, and so making them sharper would have big payoffs. Okay, so I'm going to try and get to this theorem, but it's going to take a couple lemmas. The first is a really beautiful one due to Petridis. time dilemma. And this one also has an amazing history because Rouges found a proof of this this statement or something basically close to it that is sort of extremely delicate, relying on some fancy graphs. Well, actually, it's coming from these sort of Planicket graphs. At any rate, Petridis found a really simple argument that it's just induction and uncrossing. Again, it's like these very simple combinatorial processes, and he gets an extremely powerful result. So here's the setting. A and B are finite non-empty subsets. I'm going to choose a special subset of A so that this quantity, the size of A star plus B divided by the size of A star, is minimum. Okay? So I've got A plus B, and I'm going to choose a subset of A that kind of has the sort of smallest expansion relative to B, so that when you add, so I'm asking that the size of A star plus B be equal to T times the size of A star for the smallest possible T. So I'm getting kind of the smallest growth, the smallest A star plus B in this setting. So then, well, I mean, this is true automatically. I mean, this is just true by definition, and so is this. But what's remarkable is that this holds true even if I add in any set C I want. So there's some kind of surprising control that happens here. And I mean, what's also surprising about this, as I say, is it was kind of discovered very late in the game. So this theorem's this theorem's maybe 3 years old, maybe 4 years old.
Any C from
subset of A, or
what is C comes from A?
This is for any subset of the group, any subset of the group you like. So if you just choose this subset A star of A very carefully, so that it has sort of the smallest possible expansion, then not only does it have small expansion, but for any set C you would add into the game here, you get this inequality. Okay, so the proof is induction on the size of C. When I want to be efficient with my time here. When C has size 1, this is trivially true. So for the inductive step, I can choose an element, say Z in C, and let C prime be C without Z. Now I'm going to draw a picture. Oh, maybe I better put this over here. So I'm drawing here a directed graph. The vertex set is just 2 copies of G, and I've written a plus B here because you can get from an element in here to an element in here by an edge if you can go from this element to that element by adding something in B. Okay, so now I'm really interested in this set A star plus B plus C. And how can I see that? Well, and actually C I want to split up. C I can think of as C prime together with Z. So let me draw a couple sets here. This is going to be the set A plus C prime. And over here I'm going to draw the set A plus, oh shoot, these are meant to be A stars. A star plus Z. So A star plus C prime and A star plus Z, that together is A star plus C, right? So this whole set we see up here, this is A star plus C. Now when I look downstairs, I look at all of the elements you can get to downstairs by starting at somewhere in this yellow and following an edge. That's going to be exactly A star plus B plus C. But I'm going to care about some of these sets in the middle. Let's define A prime to be the set of all elements in A, so that when I add Z to them, I stay in this set. So this is the set of all elements in A, so that when I add Z to them, I stay inside A star plus C prime. So what I claim is that this little set you see in here, I claim that that little set is exactly A prime plus Z. Right, so
All A and A or all A and A star?
Or A star? Or
oh, thank you. Shoot. Yeah. A and A star. Yeah, there is no A for our purposes anymore, really. Yeah. Yeah, I'll try not to drop that going forward. So this is the set of all elements in A star, so that when you add Z to them, you're still stuck inside A star plus C prime. Right? So, I mean, if I'm taking something in A star and I'm adding Z to it, well, that's precisely this set of elements that I can get, right? And I'm just interested in when this set of elements lands me in that set. Well, that's what I've defined A prime to be. Right, so that little set's A prime plus Z. So let's draw some things downstairs. So downstairs, this set will join down to A star plus B plus C prime. This set will join downstairs to A star plus B plus Z. And, well, in the middle here, I'm not quite sure what you'd get, but you will get all of these elements plus B. So down here, I'm going to have A prime plus B plus Z. Is it clear? All right, so I've got up top, I've just decomposed my picture. I'm going by induction. I'm just naming everything in the picture. And my graph is telling me what happens to my set when I add B. What happens to each set when you add B, right? So I hope it's clear, right? So I've got this set on the left. It grows to this one. This on the right that grows here. And I don't know quite what their overlap is going to be, but it had better contain all the elements that you can get to by starting in here and adding something in B. Right? So here we go. So the size of A star plus B plus C. Oh, sorry, I want it most. Well, I mean, I could write this as the size of this set plus the size of this set minus the size of their intersection. I mean, that would give me equals, right? I could write size of A star plus B plus C prime plus the size of A star plus B plus Z minus the size of their, let me just write size of the intersection. So that would be true with equality, right? Now, I have a lower bound on the size of this intersection, right? I know that this quantity is at least the size of this set, and that gets me the size of the intersection, right? The size of the intersection is less than or equal to this. So I can write this as less than or equal to and write A prime plus B plus Z. Should have that right? Yeah. Okay. So now, now what do I get? Well, there are a couple sets here. I mean, I've got. I mean, the size of adding Z doesn't change the size of this set, so I can freely ignore it as I can here. So let me do that. Now, this guy I know something about by induction, right? That's C prime, it's smaller, right? The size of this set is going to be at most the size of A star plus C prime, and I get a factor of T. Now, A star plus B, I mean, I know exactly how big that set is, right? A star plus B is exactly T times the size of A star. Now, what do I know about A prime plus B? Well, A prime is a subset of A star, right? You remember, A star was chosen so that this quantity was minimum. So that means the factor for my A prime set can only be greater than or equal to this. So in fact, I mean, what I'm claiming here is what I'm claiming here, that T times size of A prime is less than or equal to the size of A prime plus B. Is that what I'm claiming? Oh yeah, that's right, and this is that's right, and this is true because of this choice. Yeah, sorry. So I just had that backward. Okay, so this is true because of that choice. So then I've got this line, and now I'm in a really good shape because let's go back now. Let me toss in a couple z's. So A star, the size of A star is the same as A star plus z. The size of A prime is the same as the size of A prime plus z. But now what you see here is just T times the size of this set plus T times the size of this set minus T times the size of their intersection. So this is exactly equal to T times the size of A star plus, what am I writing? Sorry, exactly equal to the size of T times A star plus C. Right? These three sets, A star plus C prime, A star plus Z, and A prime plus Z, those are exactly this set and their intersection. And the whole of this thing was A star plus C. So that's the proof. Okay. I think I'm gonna try and keep some things on the board, and that's possibly dangerous. Now I need a real cute little fact due to Rouges, and this is called Rouges' triangle inequality. And this says that the size of A times the size of B minus C is always at most the size of A plus B times the size of A plus C. So I didn't quantify that here, but this is, I'm assuming now that A and B and C are all finite subsets of some abelian group G. So what's happening here, I mean, you'll see this sort of play out a little bit more. I mean, Petridis' lemma is sort of overly technical, and this one's, I mean, it looks a little bit more sensible. What we're getting to here is we'd like to take a set A that has small doubling and get control not only over what twice the size of A is in terms of size, but also 3 times A or 4 times A minus A or something like that. So what we're going to do is we're going to use these couple lemmas to kind of bootstrap our knowledge of our input knowledge, which is small doubling, to more sophisticated knowledge about small kind of expansion for not only twice A but other kinds of sets. And so this one's the first where we're seeing a minus in here. This is going to allow us to get control over these expressions that have minuses in them. Right? We're getting kind of bound on that. Anyway, let me give you the proof. It's dead easy. I'm going to, I'm actually going to show you that this size is less than or equal to that by just describing a function that's an injection. So for every element z in the difference set, b minus c, let's say choose elements beta of z in B and gamma of z in C, such that beta of z minus gamma of z equals z. Right? So anytime you've got some element in that difference set, it appears in that difference set somehow. There's some element of B and some element of C that I can take their difference and get z. I'm just going to pick ones. So that's my beta and my gamma. And now I'm going to define a function. So this is going to be a map phi. It's going to go from A cross B minus C to A plus B cross A plus C. Now, if I can define a successful function here and prove to you that that is in fact an injection, then I will have my desired outcome. And that's what I shall do. So phi takes the pair AZ and maps it to A plus beta of Z, A plus gamma of Z. So it's certainly a sensible function that goes from A cross B minus C to A plus B cross A plus C. Now, why is this an injection? Let me say it in words. It's easy. If AZ and A prime Z prime map to the same pair, so they map to the same pair, then, well, if you take this pair and take the difference of these terms, this minus this, you recover Z. Right? This minus this, by our definition, is Z. So if phi maps two different things to the same pair, well, those two different things had better have the same second coordinate, because I can recover Z from it. Well, but if they have the same second coordinate, then they'd better have the same first coordinate too, because of this. So in fact, this mapping is an injection, and that's our result. So phi is an injection, and that's it. Okay. So now I'm going to try and take what space I have left and prove the last thing that I need. Doing this wrong. So if the size of 2a is at most t times the size of a, then what happens is that, in fact, no matter how you take a and add it or subtract it a small number of times, that new set will have size only controlled by the size of a in a very similar fashion. Namely, if you take ka minus l times a, the size of that is going to be at most t to the k plus l times size of a. Now you'll note if you plug in k equals 2 and l equals 0, you'll know that I've given up something. I've given up a factor of t here. That's correct. I'm supposed to give that up. So this is not entirely sharp, and it's not actually. It's maybe not the most important thing in the world, but there are some people who are curious about to what extent this could be sharpened. Any rate, but for our purposes, it's very good, right? You're going from this set that has, especially if you think about the bounds that we're going to be churning out here later. Those are looking terrible. Here we have a set with just small doubling, and I'm now telling you that in fact you can kind of add and subtract a. Add it k times, subtract it l times, and you don't get something that's much worse.
So that's not a Z minus, right? It's just translation.
No, this is. Oh yeah, so I mean I maybe should have defined it, but so I mean a minus b.
Right. Minus
Yeah. 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 That's right. This is not set difference. That's right. This is. Yeah, I mean, no, it's a very. I mean, it's a very reasonable question. There are multiple logical things that you could do at this standpoint, and people do pretty well most of them. But yeah, what I mean here is this setting. So I'm taking all elements you can form. I mean, this set in words is any element you can form by adding up k terms from A and then subtracting L things from A. You're allowed to use the same thing many times. All right, so we're still controlling that. Okay. Okay, so here's the proof. I'm going to choose A star subset of A such that I'll call it now T star equals A star plus A divided by A star. Woo, is minimum. Okay, so I mean, you can see what I'm headed for. I'm going to use this property of Petridis that he gave us. So if we choose a subset of A that minimizes this quantity, then then we get control not only over the doubling, but over what happens when we start adding more complicated sets to both sides. And let me just note here that T star is going to be less than or equal to T, right? Because if you could take A star to be the whole set A, and then this parameter would be T, which is the most T. Now, now what do I want to do? Now let's look at I think this is what I want. A star plus. It should be. Yeah. So A star plus. Let's think about this. A star plus k plus 1 times the. Or actually, maybe it's better if I draw this as just a k. So I can write this as, I mean, this is just A star plus plus A plus k minus 1 times the size times A. Right, and Petridis' theorem is giving me some bound on this, right? So here A star is A star, and here A is my B. Right? Petridis is telling us that the size of this set is at most what the size of T times the A star without the B. Right? And I can just do this again and again. So if I take A star and I add k times A to it, what I get is at most T to the k times the size of A star. Now what I'm going to do is I'm going to apply this guy. What is size of A star times the size of, what do I want? K times A minus L times A. What's that guy? Well, Rouges' triangle inequality tells us that this is at most the size of A star plus k times A times the size of A star plus L times A. Right? So that's Rouges' triangle inequality for us. But now I've just seen how to bound these things. This guy is at most T to the k times the size of A, and this one is t to the L times, oops, sorry, this is A star, t to the L times the size of A star. Oh, sorry, these t's should have been t stars, yeah. I mean, but let me give up. I mean, t star was less than t. I mean, this is still true. Like, this was true with t star, but it's even more true with t, and same with this. So I can dispose of that. So so what have I got? So now I can cross off a factor of A star here, right? So what I get is Ka minus L times A is at most t to the K plus L times the size of 1 A star, and that's at most t to the K plus L times the size of A, right? Because A star is just a subset of A. And that's what I was aiming for. So that lemma of Petridis, I mean, for my purposes, it's still, I still find it confusing. It comes sort of out of nowhere. Rouges' triangle inequality kind of makes good sense. But this is the thing we really want. This is the thing we really care about, and all we're going to use going forward in the proof. So the key property here is that a set with small doubling actually has better structure. Or at least this small doubling property gets you control over all these kind of higher order sums and differences in a nice way. I mean, if you think back to the kind of structures that we have, arithmetic progressions and sets that are kind of filling out cosets. If you start adding those sets to themselves many times or subtracting them, things should start looking better and better and better, and that is indeed what happens. But what's nice for our purposes in aiming toward these proofs is that we can, thanks to these couple simple combinatorial lemmas, we get really nice control over these quantities. So okay, so that's the proof of that guy. Let me erase all this business, and that's all we'll need. So this is now I started rushing, and now I'm going to be well on time, even ahead. So there we are. Okay. So now what I want to do is use this to prove Rouges' theorem. Right. So as I say, we've got this control, and we now want to kind of take advantage of it to show that, in fact, if you're, in this very special setting where every element has order at most R, then in fact the whole set A has to be contained in a subgroup H which is not too large. That's the only reason that in a group with this kind of bound on the order of the elements, the only reason that in that setting you have small doubling is that in fact your entire set is kind of efficiently contained in a subgroup, where you can maybe using the word efficient is not the best, but it's contained in a subgroup of controlled size. Okay. And the idea of the proof here, it's very sort of simple and clever. Rouges has a lot of these sort of very simple looking statements with very, very clean and clever proofs that really help this area along. The idea is, it's really kind of a ball packing argument in my mind. So here's what we're going to do. I'm going to choose a set. Let me say, choose a maximal subset so I'm going to be choosing a subset of 2A minus A. Right, so remember, the input assumption here is that my set A has the small doubling with constant t. And so I'm going to know things about these higher order sums and differences. I'm going to be choosing now a subset of 2A minus A in a kind of ball packing sort of way. I want to choose a maximal subset so that any 2 points that I choose are far apart in the following sense. B minus A intersect B prime minus A should be empty whenever B and B prime in B are distinct. Right? So, I mean, you could sort of think I've got my big group G, I've got this sort of subset of points, 2A minus A. What I want to do is I want to kind of pick a special set of points, B, so that if you kind of draw the ball of all points you get to by starting there and subtracting something in A. I want those balls to be disjoint, right? So, I mean, conceivably you could make this sound more like a ball packing argument by really drawing a graph here. Like if you wanted to, you could draw a graph where the vertices of the graph would be elements in G, and you have an edge from this vertex to that vertex if you can get from here to here by subtracting something in A. And then what you'd be doing is you'd be picking up a bunch of vertices in this graph so that all your vertices are contained in this set, and they have this disjointness property that if you take this vertex together with its out neighborhood and do that for everybody, all those sets are disjoint. So we're getting it's a ball packing argument. Right, the nice thing is this gets us some, ball packing arguments are kind of good at getting you some rough idea of what the structure of the set is. Now, what are the key features? Well, the sets B minus A for all those elements, so that's a nice collection of subsets. Those sets are, I mean, they're just by definition, they're pairwise non-intersecting, and they're all so these things are non-intersecting. We know how big they are. Each has size of A, right? But they all live in the set 2A minus A. Oh, sorry, 2A minus 2A, right? The elements of B were chosen to be in this set, 2A minus A. If you take anything in B and subtract something in A, well, you're still going to be sitting in the set 2A minus 2A, right? So in the ball packing land here, this is oh, I guess I mean, you might be worried that this set doesn't actually contain this one, but I can assume without any significant loss that A contains 0. Like if the set A didn't contain 0, you could shift it so that it contains 0. And at worst case, I'd have to give up slightly on this constant. So for my purposes, let me just assume that A contains 0, so you do have this containment. Okay, so I've got this nice ball packing. These sets are non-intersecting. They're all contained in this. But the good news is I've got control over how big this set is, right? So I've got a whole bunch of sets, all size A, and they're all disjoint, and they live in this set. So since size of 2A minus 2A is at most, this is at most t to the 4th times size of A, right? Thanks to this bound, I know that the size of B is at most t to the fourth. Right, so this is powerful, right? So that set B that we picked up, its order is, there's no size of A in there, right? We've got a bound on the size of our set B that's totally independent of A, and that's looking very good. Right, so this set B is giving us some rough picture of the geometry, but its size is only bounded. That's very good. And conveniently, that's the last we need of this lemma, too, so I'll just erase it. So now, now what I want to do is I want to take advantage of this fact that I've got this strong bound on B. And what we're going to do is we're going to look at, right. There's this business that always happens with these ball packing arguments. I mean, ball packing arguments are wonderful when they work. You've got these balls that you've packed in. On one hand, because these balls are disjoint and they're captured in 2a minus 2a, we've got a good bound on how big they can be. The other thing is that we chose the maximal. Right? And that also has power. So let's see what that means in this setting. So what does it mean that those guys are maximal? So for every possible element you could pick in this set, say x, for every x in 2a minus a, I mean you could try and insert the ball around that point x. I mean, I know that ball you can't insert without overlapping one of these by the maximality of my choice. So I know that x minus a intersect b minus a must be non-empty for some element b. Right? I mean, if that was empty every time, then I would have tossed it into my set B. Right? So by maximality, I've got this condition. And let's read off what this means. i.e., so that means that there's some pair of elements in A, i.e. there exists A and A prime in A such that x minus A equals B minus A prime. Or I could write this as x equals B minus, or let's say plus A minus A prime. So for every x in 2a minus a, x is actually equal to b plus a minus a prime for some choice of b and a prime from my sets. But that means that x is actually in b plus a minus a. Right? So every element in 2a minus a is also in b plus a minus a. So there's something that's funny that's happened here. We've sort of, instead of a plus a minus a, I could have replaced one of those a's by a b, right? And b we have this nice control over. B is only controlled in size. So let me write down this fact. So this is just what we get automatically from the maximality of our ball packing. What we've learned is or let me just say note. What we've learned is that 2a minus a is a subset of b plus a minus a. Okay. Right, so we're going to use this in a kind of iterated sense in a moment, but first I'd like to just define a couple of key subgroups for myself. So let's let K be the subgroup generated by B and H be the subgroup generated by A. I mean, of course, if I was going to show you there's a subgroup containing A which has fairly small size, you might as well take the subgroup that's generated by A. I mean, that's the one you want. Right? It's always the smallest one. We've written this in a way that's like a little coy. But I mean, the problem is you don't you have this sort of splatter of points. Like it's not obvious what that subgroup should be, right? Anyway, so K is the subgroup generated by B, and H is the subgroup generated by A. Now the nice thing is, all the elements of my group have order at most R. And you know that, B has only t to the fourth points in it. Well, if you have only t to the fourth points, and they all have order at most R, and you're an abelian group, you can't get too many elements. Namely, the size of K is at most R raised to the power t to the fourth. Right? For each, this is a generating set. Even if they're totally independent elements that are all order R, you only get a subgroup of this size. So that subgroup generated by B, even that guy we have control over, and conveniently we're seeing something that's looking promising over here. So now right. So now what I claim is H I can express as a union as J goes from 1 to infinity of sets of the form J times A plus A minus A. Right? There's not much. This is immediate, right? Because I'm letting J run from 1 to infinity. You can just, every element in A, in H, you can get by adding up elements of A enough times, right? But what we've learned is that, 2A minus A is a subset of B plus A minus A. And in fact, that just iterates. If I give you, if I had given you 3 times A minus A, this is equal to A plus 2A minus A, which is a subset of, 2A minus A, that's a subset of B plus A minus A. So this is a subset of this is a subset of 2A plus B minus A, right? So I can just repeat this. As long as I'm adding in, I can say this slower and properly by induction. Let me do that. If you take something like K times A minus A, this is equal to K minus 2A plus 2A minus A, which is a subset of K minus 2 times A. And I know that 2A minus A is a subset of B plus A minus A. So what's happening here is K times A minus A is a subset of K minus 1 times A plus B minus A. So if I have a term that looks like this, so long as K is at least 2, I can replace one of those A's by a B. And I can just keep going, right? So now, now just put this B to the side. Now you have K minus 1 times A minus A. You can repeat. So in fact, this whole thing is a subset of the union as J goes from 1 to infinity of, so now I will write this as J minus 1 times B plus A minus A. Oh, sorry, I can write it as J times B. So this big union contains my subgroup H. But what I know is that anytime you have an expression of this form, as long as J is, you can just replace these JAs by JBs. You can just do it one at a time using this property until you get here. But now this guy, this is just a subset of, J times B. You're letting J grow and grow and grow. But we know that the whole subgroup generated by B is just K. We controlled the size of that. So this is a subset of K plus A minus A. Right? And right, okay. And now, so what I've learned is that the size of H, the size of H is at most this, but that's at most the order of K times the order of A minus A. Right, now I'm using the totally naive multiplicative bound. And by that lemma that we had earlier and just erased, you know that if A has doubling with a constant of t, then A minus A, the size of A minus A, is at most t squared times the size of A. And that's the bound we wanted, because the size of K was r times t to the 4th power. And that's the proof. So, yeah, so I think I want to emphasize that this is all very, very sensible combinatorics here, right? We've done a couple of kind of intersection union induction arguments. What we see here is really a ball packing argument, and what's dropped out is this powerful theorem that tells us that it gives us a rough structure theorem for what it means for a subset of a group with this bound with small doubling. So if you're in any group with this kind of bound and you look at any set that has small doubling, then we have a rough structural description of why that happens. And yeah, this really is just the tip of a giant iceberg. But I think we'll stop there for today. So thanks.
Yeah.